looked at conjugate acids and bases. This thing's kind of hard to see. It gets right in my eyes. All right, that's better. So we can make conjugate acids and bases. When given a particular molecule, we can make the conjugate acid or base by adding or subtracting H+. So we're going to add or subtract a hydrogen, but also that charge, that positive charge. So we're going to end up being more negative or more positive, depending on if we're subtracting or adding. We looked at some names of some acids, the non-oxygen acids and then the oxygen acids, and we saw how those were named in different ways. And then we looked at this idea of equilibrium, that as a reaction occurs, you lose the products as they're forming reactants, you form the reactants, and then at some point they don't even out as if you have the same of both, but they stop changing. And equilibrium is that point at which it stops changing. But then we also said that we can affect the equilibrium by putting a stress to one side or the other. So we can add more of one side, which will push things to the other side. We can take away of one side, which will lower things from the other side. It's much more like, you know, I don't know. I feel like I can emphasize my points better with these giant fins. All right.
Do you mind if I'm recording?
No, it's on the computer anyway. Oh, like because of the Penguin thing? That's fine. It's fine. All right, so we stopped last time talking about strong and weak with regards to how they dissociate in solution. And so we're going to pick up with that and talk about how we measure the acidity or basicity of a solution using pH. Okay. So we defined the strong and weak acids and bases. Another thing to note is that there are only 6 strong acids. That is, acids that dissociate completely in water, that break apart completely into ions. There's only 6 of them. A couple of them are the ones that you need to know based on the list on Blackboard. So that would be HCl, hydrochloric acid, HNO3 nitric acid, and H2SO4 sulfuric acid. And then there's 3 more. Perchloric acid, hydrobromic acid, and hydroiodic acid. You don't need to remember that those are the strong acids, but I just want you to know that there are only 6 truly strong acids that completely dissociate in water. All the other acids are going to have this equilibrium where they're going back and forth, and there's some whole molecules and some ionized molecules, or some ions. So remember the way that we describe our acid-base equilibrium, like this, where you've got a neutral acid plus water forming 2 ions, hydronium ion and fluoride ion. In a weak acid situation, that's going to be going back and forth and mostly backward. In a strong acid situation, that goes entirely forward to form only ions. So when you look at a solution of HCl, you will not find any intact HCl molecules. But when you look at a solution of HF, you will find mostly intact HF molecules and just a little bit of hydronium and fluoride. That's what we mean by strong and weak. Remember also that strong acid has nothing to do with corrosive acid. Strong acids aren't more dangerous than weak acids. Those words, strong and weak, only apply to how they behave in solution and how they break up into ions, not whether or not they can hurt you or burn you, whether or not you're a penguin. All right, so let's look at how we measure acidity of solution. So to find out how acidic a solution is, we need to think about how much hydronium there is in that solution. So I'm going to write down a really weird chemical equation. What happens if two water molecules do an acid-base reaction with each other? What would you form? So think about what it means to do an acid-base reaction. What does it mean to do an acid-base reaction? What changes? What happens if an acid and a base react with each other? Go back to the very beginning of these notes. What happens in an acid-base reaction? How did we define acids and bases? Yeah, it donates or accepts a hydrogen. So if that happens between these two molecules, what are the products going to look like? Right, yeah, one of the waters is going to gain a hydrogen and one of the waters is going to lose a hydrogen. It doesn't matter which one's which because they're both water, but one of them's going to gain, one of them's going to lose. So the products of that are hydronium and hydroxide. If one of the hydrogens gains H plus and the other one loses H plus, that's what you'd end up with. And this actually happens in water. This happens in water, but it happens only a little bit because we know water is mostly not ionic. And if we try to conduct electricity through water, it doesn't really conduct electricity for pure water. So that means that if we were to draw these arrows, it's really more like a little bit forward and mostly backwards, mostly like that. And you can actually measure this. So you can set up a device that we're going to use in lab next week called a pH meter. You can measure the amount of hydronium ion in solution. And if you measure that, you'd find that the concentration of hydronium, which we write as brackets like this. So whenever you see something in brackets, brackets signal that we're talking about the concentration of. So the brackets mean concentration. The concentration of hydronium ion in pure water is 1 × 10⁻⁷ molar, which is a very, very small number. So if we were to write that out, not scientific notation, it would be 0.000001 molar. It's a very, very small concentration. Normally in the last chapter, we dealt with concentrations of like 1 molar or maybe 0.1 molar. So to go 0.000001 molar is like a tiny, tiny amount. So there's very, very little in there. And since this reaction produces just as much hydroxide as hydronium, there has to be just as much hydroxide in there too. So the concentration of hydroxide, the molar ratio in the equation is 1:1. So the concentration of hydroxide has to be the same. So in pure water, there's exactly the same amount of hydronium and hydroxide ions. And so we call it neutral. They're totally balanced. Let's see, how can we write that? We can write it like this. The hydronium concentration equals the hydroxide concentration. So the solution is neutral. When those two concentrations are the same in a solution, we call that solution neutral. So when we have an imbalance in those two concentrations, that's when we call the solution acidic or basic. If we had more hydronium, so when the hydronium concentration is greater than the hydroxide concentration, there's more hydronium than hydroxide. Then we'd call that solution acidic.
What are you studying so you know how to do what you're doing right here?
What do you mean?
What am I concentrating on doing? Am I knowing the H3O plus the OH negative? Is there, I mean, because I don't even understand what you're writing.
Right now, we're just talking about definitions. So we're saying, how do we call something acidic or basic? And we're saying we're going to look at that equation, that dissociation of water. And we're going to say if they are equal, if there's just as much hydronium and hydroxide, we're calling that neutral. If there's more hydronium, we call that acidic. If it's more hydroxide, we call it basic. We'll get into how we assign that numbers next. So what does it mean for a solution to be acidic or basic? It means that there's an imbalance in the hydronium and hydroxide concentrations. Okay. So we can write the opposite here. When there is less hydronium than hydroxide, we call that solution basic. All right. So if we want to know if a solution that we have in front of us is acidic or basic, we need to measure the hydronium concentration, measure the hydroxide concentration, and then see which one's greater. But there's kind of an easier way to do that, and that's to look at something called pH. You've heard of pH before, probably at some point with regard to something. But the pH is actually a specific definition. It's a mathematical operation. It is the number that you get when you take the negative log of the hydronium ion concentration. So you measure the hydronium concentration, you put it in your calculator with that little log button, and you get this number called the pH. All right, so why? Why do we use this log? Anybody know? What is log? What is the log for? We all have calculators. What's the log thing do? What's that operation for? Why is that an important mathematical operation? You know there's a button there, right?
Yeah.
Yeah, okay. What's it for? Just tell you to press it sometimes? Yeah. It's always good. Just push buttons. People tell you to. So you got add, you got subtract, you got multiply, you got divide. So what does log do? All of them at once? Yeah. Yeah, I mean, this is not an unexpected response. Every time I ask this question, everybody's just like, I don't know. It's like on the calculator. Who knows? It just says log. A log is a way of finding an exponent. You know what an exponent is? The little tiny number up on the top of a thing, like when you raise something to a power. The log gives you that number, returns that number as a result. So if you take quick log lesson, if you take the log of 10 squared, you get 2. So the answer to a log expression is the exponent. And specifically, it has to be of 10. So it has to be, it's called a log base 10. There are other types of logs. This log is a log base 10. That's the calculator one. That exponent could be negative. That makes a small number. You get that exponent each time. The number doesn't have to be written as an exponent for that to work. What is 10 squared as a number? Ten times 10? 100, right? So if you took log of 100, you'd still get 2, because 100 is 10 squared. Right? So you take the log of a 10 to the something, and you get the something back. That's what logs do. All right. So in effect, what that does is it turns a range of numbers where you're continually multiplying 10. So like a series of numbers like 10, 100, 1,000, 10,000, 100,000, million, you keep adding zeros, and it turns that into integers. So it turns that into 1, 2, 3, 4, 5, 6 by giving you that exponent. And the reason that it's useful in these situations is because with weak acids, the concentrations are always these tiny, tiny numbers. So 10 to the minus 7, 10 to the minus 5, 10 to the minus 12, these really, really small numbers. And so we can better put those into a scale if we just rearrange it mathematically to be like 1, 2, 3, 4, 5, 6, 7, because those are easier numbers to deal with, rather than having to deal with these 10 to the whatever numbers all the time. So let's try one. If you want to know what is the pH of a solution where the hydronium ion concentration is 10 to the minus 7th molar. So that's like what we just talked about in pure water. How do we find the pH? So to find the pH, we evaluate that equation above, the negative log of the hydronium ion concentration. We say the pH is the negative log of that concentration. And then we can evaluate it. Based on what we just talked about with the log, we can say, all right, the log of 10 to the minus 7 is minus 7, right? We just get the exponent there. So that would be negative 7, which is 7. So that's where that negative comes from in that expression. You take the log, you get the exponent, you flip the sign, and you got a positive number. So our pH scale can be positive numbers along, small positive numbers instead of these big, weird exponent numbers, scientific notation numbers. All right, so the pH is 7. What happens then is that as that hydronium concentration increases, the pH ends up going down because we're flipping the negative to a positive. So what's a larger number? 1 times 10 to the negative 7 or 1 times 10 to the negative 3? What's a bigger number, 10 to the minus 7 or 10 to the minus 3? Minus 3, because 10 to the minus 7 is 0.0000001. 10 to the minus 3 is 0.001. So it's a much larger number. If we evaluate the pH of that, remember we just take that exponent and flip the sign. So the exponent is minus 3, the pH is 3. So we end up with a number that is less than 7, but that corresponds to a higher hydronium concentration. All right, so just make sure that you're thinking about that, keeping that straight in your head, that the lower pH is actually the higher hydronium concentration, the greater concentration of hydronium. Now, if we're in a water solution, the hydronium and the hydroxide concentrations are complementary at equilibrium. So if we said before, if we have a pH of 7, that means that our hydronium and hydroxide concentrations are equal and we're perfectly neutral. If the hydronium concentration goes up to 10 to the minus 3, which makes the pH 3, the OH concentration has to go down by the same amount. So one way to say that is the pH and the pOH always add to 14. So you can do the P thing to the OH concentration just like the hydronium concentration. You can do the negative log, and then you get the POH. And those two numbers added together are always going to be 14. So if your pH is 3, your POH is 14 or is 11, right? Because 3 plus 11 is 14. All right. So let's see how this works with the example from the book, and then we'll look at the scale. This will be on the quiz on Tuesday, yeah. If you dress as a penguin, it makes you feel smarter. Yeah, a week from today. We'll do a quiz. Because there's no quiz this week. Right. All right. So here's the types of things that you should be able to do. I'm on the wrong page here. 343. We'll go through some of these together, and I want to show you how to use a calculator for these too. What do I do? Yeah. If a number is less than 7, that's acidic because it has more of a hydronium concentration. Yeah. Yeah, we'll talk about that scale in a minute. But let's practice some calculations while we're talking about these. All right, calculate the pH of each solution given the following hydronium or hydroxide values. So the first thing to note is these two on the left, A and C, we should be able to do those without getting calculators out. The other ones we'll all have to use calculators for, and I'll show you how to do that. In this class, we don't require anything beyond a standard 4-function calculator, so you won't see problems on the quizzes or exams that use log, that require, so only the ones that you can do by hand without the calculator you'll see on quizzes and exams. If you have a calculator and you want to use it, that's fine, but you won't need it. All right, so let's look at that first one. The hydronium ion concentration is 1 times 10 to the minus 4 molar. So what's the pH? 4, right. We just look at that exponent, and that's the pH. Let's go down to C, since that's another one that we can do without a calculator. If the hydroxide concentration is 1 times 10 to the minus 5, what's the pH? It's not 5. It's 9, right? Because 5 would be the pOH. So if we calculate the pOH of the hydroxide concentration, we get 5. The pH and the pOH always have to be 14, so the pH would be 9. See how that works? So when you're given the hydroxide concentration instead of the hydronium, you have to subtract what you get from 14 to get the pH. All right, let's look at one of these now where we have to use a calculator and see how that works. Let's look at B. So in this case, we can't just say, so the hydronium concentration is given as 3 times 10 to the minus 9. We can't just say that the pH is 9 because of the 3 there. It's 3 times that. So if it were 1, then it would be just 9, but it's 3, so it's not. So we have to use a calculator for that. Depending on what kind of calculator you have, there's various ways to do this.
Can I stop you?
Yeah.
Where did you get 14 C?
When the two concentrations are equal, they each are at 7. That's from this here. Okay. So in pure water, both concentrations are at 7. So that's a pH of 7. So when the pH goes down, the OH has to go up and vice versa. So they always, 7 plus 7 is 14. They always have to add to 14, the pH and the pOH. All right, so I'll show you with the calculator on here, and you can adapt it accordingly. If you're doing this on your homework at home or something, if you have a scientific calculator, if you have a graphing calculator, it's easy. You just type it in directly. If you don't have a graphing calculator, but you have a regular scientific calculator, or like the one on your phone, if you turn your phone sideways, the log thing comes up. It's a little different because how those work is, even though the expression is negative log of something, you can't type it in that way. You have to put the number first and then push log to take the log of it. So on a calculator like this, I would go, I would go -9, and then I would raise 10 to the -9. So you kind of have to do it backwards. So there's 10 to the -9. Then I'd go times 3, because there's a 3 out in front. And then I would take the log of that whole number, and then I would flip the sign on it. So I'd get about -8.5. Or I'd get 8.5 for the pH. That's a little weird if you're not used to that kind of a calculator. Again, don't worry too much about the calculator ones, because when they just have 1 at the beginning, which is what we'll see on quizzes and exams, you can just look at the exponent and put that down. But if you're going through the homework, you want to check yourself with the calculator, that's how you do it. If you have a scientific calculator, or I think the iPhone calculator does this too, or I'm sorry, a graphing calculator. Can I borrow this? You should see a little thing that says EE, like capital E, capital E. And this is a TI-84, and it's above the comma in blue. So the way you use that is if you wanted to type in 3 times 10 to the -9, you can just type 3 and that little EE, makes a little capital E there. And then you just write -9, and that means 3 times 10 to the -9. So that's a lot easier because you don't have to do the times 10 to the, you don't do parentheses or anything, it just keeps it together. But yeah, so you're going to go 3, and then that little E, and then -9.
2 times?
No, the button, I don't know why. The button says EE, but you just push it once and it puts 1 E in there. Yeah. So you just push 1. And then whatever you want that exponent to be. So -9. So on this calculator, you go. Oops.
But this shows error.
Where is this fancy? Yeah, you don't need the so you go log, negative log of that. All right, if you want me to show you how to do that on your own calculator, we can do that during lab or whenever. I'd be happy to show you how to do that. Okay, so that's how you calculate that. Let's look at what that actually means, though. All right, so here's the pH scale. Let's see if I can make this a little bigger so we can see it better. If we'll look at the 2 halves of the scale separately. So here's the acidic side. You've got neutral water, pure water at 7. And then as those pH numbers go down, you get more and more acidic. So you've got milk just below, just to the acidic side of water. Then, other bodily things are down there, although blood is a little bit above 7. Down to your very acidic things like carbonated sodas, vinegar, lemon juice. The hydrochloric acid in your stomach is very acidic. And then the very bottom of the pH scale at 0 is a hydrochloric acid solution, a 1 molar hydrochloric acid solution. So if you put 1 mole of HCl in a liter of water, you've got a solution with a pH of 0. On the other side of neutral, you've got things like drinking water. So drinking water coming out of a faucet or a bottle has minerals in it. usually like some calcium, magnesium, stuff like that. Sodium makes it taste better. That is giving it a little bit of basicity. So like, I don't know if you can try this at home. If you have a little bit of leftover colored, something that's naturally colored like wine that's red, or like some beet juice or cabbage, that kind of thing, and you put your tap water in it, it'll actually turn kind of blue because it's an indicator, and it's the basicity of the water is turning that blue. If you go down to more strongly basic things, cleaning solutions are mostly bases. So things like ammonia, bleach, detergents, that kind of stuff are basic. Lye is the name that we give, LYE, to a 1 molar sodium hydroxide solution. Well, sodium hydroxide in general is lye. That is an extremely strong cleaning solution. If you've ever had to like soak a carburetor parts, or like really like get corrosion off, really strong corrosion off metal, you might use sodium hydroxide lye solution. Drain cleaner is way down there at super basic.
Is that what they put on roadkill too?
On roadkill?
Yeah. Isn't that called lye? Right?
That might be lime.
Are you sure?
I have no idea. Let's look it up. What do you put on roadkill? What chemical I do not see that. What is the goal of the thing when you put it on roadkill?
Like eats it. I know they do it in the country because my friends live in the country.
Okay.
So
It's like a white powder? Or it's like a liquid?
it's like green.
A
They
green,
put it on top of
like a powder.
Yeah. And then it just eats it away, and then and it like eliminates the odor and stuff, so it's I just thought it was the same.
I don't know. My guess is it's not, because that would be maybe an environmental hazard, because sodium hydroxide is so corrosive. Like if somebody were to touch it with their skin, they could get a burn from that. So that's probably not what that is. I mean, I'm sure it's some kind of chemical thing that, like you said, neutralizes the smell, probably pulls some of the water out to help desiccate the body. But I don't think it would be a really strongly basic thing. Maybe, I don't know. We'll have to look that up. I've never heard of that. I've never seen a roadkill with a bunch of stuff on it. One time my parents drove over a deer carcass and it like exploded under the car.
Oh, yeah.
And it just smelled for like a week. It was terrible. All right, what were we talking about? Oh yeah, acids and bases. No, that's okay. Thank you. I hadn't thought about that. So one of the other misconceptions with acids and bases is that acids are dangerous compared to bases, and that's not really true. The extremes of both scales are very, very corrosive to your skin, and you want to make sure not to touch them. Sodium hydroxide, which we've used usually in lower concentrations, but very concentrated sodium hydroxide can be just as corrosive and dangerous as acid. So a couple of things with the pH scale that we should know about. Blood has to be kept in a very narrow pH range. So it's not good enough to just say blood is neutral, blood is 7. Blood has to be 7.35 to 7.45. If it's outside of that range, you're in trouble. You're in a situation called acidosis or alkalosis, which we'll talk about when we get into buffers. So blood pH has to be very carefully controlled, which it is in your body chemically with carbon dioxide. Again, we'll get into how that works. But one of the interesting things that's popular lately is the idea that what you eat controls the pH of your body. Have you heard this? Like you shouldn't eat acids because they'll make your body too acidic, or like that kind of stuff, or you should drink a lot of cranberry juice because it'll make your body more basic. Like that's all nonsense, because what happens is, remember, your stomach is really strongly acidic. Your stomach is a pH of about 1. So anything you eat, assuming you're eating through your mouth, is going into your stomach and instantly in a very acidic environment, which helps break it down. So then, of course, it goes through the intestines and all that stuff. So the idea that you can affect your pH of your blood or your like metabolic pH through what you eat is wrong. Your body regulates those things. It has nothing to do with what you eat. It sounds good because you could say, oh, your blood has to be a really specific pH. So if it goes out of that range, you're in trouble. But you can't actually control that by eating one thing or another. So that's one of those ways where we take like a true scientific fact, like your blood pH has to be carefully controlled, and then kind of extend that to things that don't make as much sense, which is, well, then we control them by eating this and not eating that kind of thing. As we'll see, there are different factors to blood pH, respiratory and metabolic factors. So if you're having issues with liver malfunction, kidney malfunction, that can affect your blood pH. All right. So for a nice kind of summary table of all the stuff we've just been talking about, on the bottom of page 343, there's this table that relates hydronium hydroxide concentrations with pH. So you can see on the left, as hydronium concentration goes up from bottom to top or down from top to bottom, pH, or let's just stay in the same direction. We'll stay from top to bottom. As we go from top to bottom, the hydronium concentration goes down because it's going from 1, 10 to the 0 is 1, to 0.1, to 0.01, to 0.001, to 0.0001, and so on with every step. The pH goes up, and the hydroxide concentration goes up. So they go in opposite ways. The hydronium goes down, hydroxide goes up. pH increases with more base or with less acid, however you want to say that. The important thing is that you remember those trends, that you remember that low pH means acidic environment, high pH means basic environment. Okay. So we should be able, without looking anything up, we should be able to do a problem like this. All right, you'll see something like this on the quiz on Tuesday too. So we got acidic, basic, or neutral. Soda, 3.22. Acidic, yeah. Shampoo, 5.7. That's going to be on the acidic side. Laundry detergent at 9.4. Basic. Rain, 5.83. Acidic. Honey, acidic. And cheese is acidic, yeah. So generally, when we talk about neutral, the book says neutral is 7, exactly. You'll find some disagreement with that among other references. So some people would say a range of 6 to 8 is neutral. Ultimately, what we call that doesn't really matter. So like, I would never ask you, is a 6.5 solution acidic or neutral? Have you pick acidic and then mark it wrong or something? You know what I'm saying? Like, it would have to be outside that range because you can find some competing definitions of, do you call only 7 neutral or do you call around 7 neutral? So I would say around 7 is neutral, but technically anything below 7 has an imbalance of hydronium and hydroxide, as does everything above exactly 7. All right. So any questions about pH? Like that? Okay. The last thing, or the last couple things we're going to talk about is neutralizations and buffers. But I think I want to hold that off until Thursday. So we have plenty of time for the lab. I'd like to get out a little early today for trick-or-treating. So I'm not going to go trick-or-treating. I mean, I'm not going to get candy and take the kids trick-or-treating. So so let's take a break now and come back to start lab in about 15 minutes, if that's all right. And then if you're looking for something to do, remember, you don't have to finish your report, but if you can get your data posted, you can do it on your phone or whatever, that would be good, and then everybody has it. And then if you need a couple minutes to finish the pre-lab or whatever, go ahead and take those, and we'll start the lab up about 1:30.
that.